we're asked to show that there is only one solution for this equation, positive integer solution. So a to the power of n plus 1 minus a plus 1 to the power of n equals 2001. So first of all, I noticed that if I simply expand it, it'll give me a to the power of n plus 1 minus a to the power of n minus n times a to the power of n minus 1, so on and so forth, minus n times a minus 1 equals 2001. Now if I plus 1 on both sides, it'll give me 2002. Right? So here we have every term has a factor of a, so which means a divides left hand side, which is a divides 2002, right? Which happens to be 2 times 7 times 11 times 13. Now next I say, because 3 already divides 2001, then if a is divided by 3, what's the remainder? If we say the remainder is 0, what's going to happen? Because this is already divisible by 3. Assuming a is divisible by 3 also, so is this term. So this term has also to be divisible by 3. But it's impossible, because how can you have a, because here the remainder is 0. A plus 1 divided by 3, remainder has to be 1. Cannot be divisible by 3. So same reason, remainder cannot be 2, because then a plus 1 are definitely divisible by 3. Right? So is this term. So this term has to be divisible by 3, which is impossible. So the only possibility is 1. So next I say, I claim n has to be even. The reason is because since we already know a is congruent to 1 mod 3, which means a plus 1 is congruent to 2 mod 3. Or you can say negative 1. Right, same thing. Now here, since raised to the power n plus 1 on both sides, and so a to the power of n plus 1 also congruent to 1 mod 3. All right? So when you have a plus 1 raised to the power of n has to be congruent to negative 1 to the power of n mod 3. Right? Then on the left hand side you add them up. A to the power of n plus 1 minus a plus 1 to the power must be congruent to 1 minus negative 1 to the power of n. At the same time, the right hand side is 2001. So 2001 is divisible by 3. Right? So congruent to 0 mod 3. So imagine if n is odd. Right? So this will be a negative 1. Right? So 1 minus negative 1 be 2. That will be impossible. Right? So n has to be even. Right? If it's even, then it's positive 1. So 1 minus 1 equals 0. So n has to be even. Right? So n has to be greater than or equal to 2, because it requires positive integer. Right? Next, I say a must be odd, because if we suppose if a is even, what's going to happen? Right, if a is even, okay, then I let a equal 2k. This time I use the divisor of 4, mod 4, see what happens. Okay. So this time, so this time a to the power of n minus 1 is equal to, so let's use congruent, so equal 2k to the power of n minus 1, n plus 1, of course. Congruent to 0 mod 4, obviously, because 2 raised to the power of n plus 1 divisible by 3. Right? So then it's a plus 1 to the power of n. Right? So then a plus 1 is equal to 2k plus 1. Here k is some positive integer. So a plus 1 to the power of n, right? This time equal to 2k plus 1 to the power of n. What is that? 2k to the power of minus plus n times 2k to the power of n minus 1 all the way. N times 2k plus 1. Notice, because n is greater than or equal to 2. Right, is an even number. So each term obviously is divisible by 4, right, except this term. So it has to be congruent to 1 mod 4. Right. So like I said, this is congruent to 0 mod 4. This is congruent to 1 mod 4. Right? If we minus, take their difference. Yep. So take their difference. A to the n minus a plus 1 to n, right? So 0 minus 1, negative 1. At the same time, equals 2001. So 2001, which is congruent to divided by 4. Remainder is just 1. Which is impossible, right? So like a cannot be even. Right? So a has to be odd. So far we reached those conclusions. So a divides 2 times 7 times 11 times 13. That's the decomposition of 2002. So, and also a is congruent to 1 mod 3. N is even. N is greater than or equal to 2. A is odd. So we immediately see that we can narrow down our possibility. Right? A is odd. So a divides, actually, we don't need 2 here. Doesn't contain 2. So from here on, I say, this time let's use the divisor of 4, mod 4, see what happens. All right, so 2001 divided by 4, remainder is 1. All right, if I say, let's let a equal to 2k plus 1, k some positive integer, because we know a is odd. So this time a plus 1 to the power of n is equal to 2k plus 2 to the power of n. That is 2 to the power of n times k plus 1 to the power of n, of course. That is congruent to, because n is greater than or equal to 2. So if divided by 4, so remainder is 0. Mod 4. Right? And also because a to the n plus 1, what is that? A to the power of n plus 1. Right, that is 2k plus 1 to the power of n plus 1. that is 2k to the power of n plus 1 plus n plus 1 times 2k to the power of n plus n plus 1 times 2k, last term, plus 1. Right? So this time, here I can just rewrite it as 2nk plus 2k and plus 1. Right? So obviously here, every term, if we, like I said, we divide it by 4. So you see, n is greater than or equal to 2. So here we have 2 to the power of some positive integer. So again, here, same case. So up to here, so 2n, it's okay, divisible by 4. Up to here. So here, every term is divisible by 4, except this one. Right? So immediately I say it's congruent to, these are congruent to 0, 0, 0, 0. So congruent to 2k plus 1. But what's 2k plus 1? Right, that's A, exactly. Okay. Mod 4. Right, that's A to the power of n plus 1. And so, okay, I use this one, then minus this one. Right? So A to the n plus 1 minus A plus 1 to the power of n. Right? Like I said, this right congruent to A. Right? So this congruent to 0. Right? 0. Then right hand side 2001. Right? Divided by 4. Like I said, remainder is just 1. Mod 4. So which means if divided by 4, so A is congruent to 1, mod 4. So two key pieces of information. 1, so far. So A is congruent to 1 mod 3. And A is congruent to also 1 mod 4. Okay. So what can we use that for? Okay. I said we can further narrow down our possibilities. So we already eliminated, get rid of the 2 here. So it's some combination of those 3 factors. Could be 1, 2, 3. Right? But the thing is that if you look at 7, right, mod 3, right, congruent to 1, and when you look at 13, mod 3, also 1, right? So those 2 don't worry, because when they multiply by any remainder, it's gonna make them the same. So have a look at 11, mod 3, congruent to 2, right? So that's the only problematic one. Because A is known to be congruent to 1 mod 3, right? The only thing you cannot have is this one, right? Those 2 are fine, right? Because 7 times 11 times 13, right? Here. Right? So you cannot have 11 here. Right? 7 times. So we narrow down to this. Right? Okay. So mod 4, let's have a look at that. Right, for example, 7. Mod 4, right? Remainder should be 3. Right? 13, mod 4, right? Remainder is just 1. This is fine. This is fine because A is congruent to 1 mod 4. But the only problem is this one. Right? How can it be 3? Right? A cannot contain 7. Cannot contain 7. Here. So could A be 1 in this case, right? A could be 13. Right? Could A be 1? No. If A was 1, so 1 minus 2 to the power of some, 2, 4, 6, right? Cannot be 2001. It'll be negative, in fact. So after we narrowed down our possibilities, we finally reached that A divides 13. But A cannot be 1, like I said. So A has to be 13. Right? Only one answer. We don't need that. So the only thing is that we have to determine the value of n. Right? Here I say n can only be 2. Cannot be greater than or equal to 4. Because if n is greater than or equal to 4, this time I use mod 8. Right? What's going to happen? Like I said, so A is 13 already. So 13 to the power of n plus 1 minus 14 to the power of n. But 14 to the power of n is in fact 2 to the power of n times 7 to the power of n. Right, congruent to things like I said, here I assume n is greater than or equal to 4. So this term has to be divisible by 8. Right? This mod congruent to 0, mod 8. So this is congruent to this. Later it will be congruent to 2001, which is congruent to 1, mod 8. But before that, I have a look at this. So what happens with this? So 13, when I have a look at, because 13 first, congruent to 5 mod 8. Right. Then, like I said, so I let n equal to 2k. So 13 to the power of n, this time, 13 to the power of 2k. 13 to the power of 2. Okay. But since this is, so I immediately deduct 13 to the power of 2 is congruent to 5 times 5, 25. 25 divided by 8, remainder is just 1. Right? Mod 8. Okay. So this is, right, this congruent to 1. Right, so this comes to 1 to the power of k. That's congruent to 1, mod 8. So what happens now is that 13 to the power of n plus 1. Right? Right, this 13 to the power of n is already congruent to 1. Multiplied by another 13. Congruent to 5 times 1, 5. Mod 8. Right. But like I said, the right-hand side, don't forget, right? That's the right-hand side. Right-hand side, 2001. Right? If divided by 8, which is easily verifiable, remainder is just 1. So, which is a contradiction, of course. So which means n cannot be greater than or equal to 4. All right. It's exactly the reason which leads to the fact that 2 to the power of n in this case is already, 16, 32, whatever. So, right, divisible by 8, right? That's exactly the reason that which leads to all of this, right? Leads to the contradiction. Right? So we cannot have that. So, which means n has to be 2. That's the only solution.